Welcome to section 4.8, which is the last section in chapter 4 and the last section about derivatives. So here we are going to talk about the idea of a tangent line approximation. And what that means is if you are given a function that is either too complicated to figure out, or if it's a real-life problem where you don't know the function itself, then it might be useful to use an approximation rather than the function itself. And the way it works is, given a certain function like this one, let's assume that we don't know the equation of this function, but we know a point and we know the slope at that point. And that's a fairly reasonable assumption. Let's say you're on a road, you know where you are on the road, you know your altitude, let's say, and it's not so hard to figure out the slope of the road at that point, but you might not know the exact equation of the road itself. If you know a point and the slope, what you can do is find the tangent line. That's easy to find, we did it many times. And so if you're wondering about how high is a point nearby, then you can find an approximation by finding the point on the line that is tangent. So in order, you are given a function, or you know there is a function but you don't know its equation. You know a point and the slope on that function, and you wonder about another point on the function. However, you're unable to find this point. So the best you can do is to figure out the equation of the tangent line to the point, to the original point that you are given, and then calculate the position of the point for the x value that you're looking for. So you will find this point instead of that point, but it's pretty good. Now notice that it's only pretty good if you stay nearby. If I go really far away, the result I would get instead of the point here at the end of the function would be drastically different, so it would be a terrible approximation. But as long as you stay near the original point, you're going to have a good approximation. So for example, nobody knows out of the top of their head what ln of 0.9 is. If you're not given a calculator, you're not going to be able to figure out what ln of 0.9 is. However, there's a good choice we can make, because there's a point we definitely know. We know that ln of 1 is equal to 0. So if I choose x equals 1, I'm happy because it's close to 0.9. I'm happy because I know that ln of 1 equals 0, so I have the point 1, 0. And I'm also happy because I'm able to find the slope at that point 1, 0. All I need to do is to calculate the derivative of y equals ln of x. It's y prime equals 1 over x. So by plugging x equals 1 in, I find that the slope is 1. That allows me to build a tangent line to this point, and it's going to be y minus 0 equals the slope times x minus 1, and so it's simply y equals x minus 1. So my approximation is not going to be the point on y equals ln of x, it's going to be the point on the tangent line to the curve. So ln of 0.9 is approximately x minus 1, so it's approximately 0.9 minus 1, so it's approximately negative 0.1 by hand. So by hand, purely by hand, you can say that ln of 0.9 is approximately negative 0.1. If we use the TI-Nspire, we can find that the actual value of ln of 0.9 is negative 0.10536. So I would say we didn't do too bad. We're very close. We are 0.05 away from the actual answer. So the first example showed you that we didn't have the function itself. We weren't able to find the value because we were unable to actually calculate ln of 0.9. In the second example, we just do not even have an equation for f of x. We know that f of 5 equals 2, f of 6 equals 5, f of 7 equals 24, and we know the derivatives at these 3 points. The question is, find an approximation for f of 6.1. So I'm going to choose x equals 6 as my anchor point. And why I choose that is that 6 is the closest to 6.1. So I know the point is the point 6,5. I also know the slope at x equals 6. The slope is equal to 3. So I can build a tangent line, which will be y minus 5 equals the slope times x minus 6. So my tangent line is y equals 3x minus 13, and that tangent line is going to be a reasonably good approximation of what f of 6.1 is. Maybe it's not, but that's the best we can do. At x equals 6.1, my tangent line says that f of 6.1 is approximately 3 times 6.1 minus 13, and that would be 5.3. That's it. I can't be sure it's great because I have no additional information, but that's the best I can do. Last example, find an approximation for the cube root of 28. Again, this is impossible to actually figure out without a calculator, so what we're going to do is we're going to use a tangent line to approximate what this might be. And what's a great choice of a point that we can use as an anchor nearby? We can choose 27. Because we know what the cube root of 27 is. The cube root of 27 is 3. So we're going to use that point to fix our tangent line, and then it won't be too hard with a tangent line to find what the value is for 28. So for x equals 27, I know that the cube root of 27 equals 3. I could have put a little 3 here. What about the cube root of 28? It's a little beyond, so just by eyeballing it, I could say it's maybe 3.05. But what we're going to do is we're going to actually find the equation of a tangent line, so it's a little better than eyeballing, and see what that yields. So I have a point, 27, 3, and then I need to find the slope at that point, so I take the derivative of y equals cube root x, and I plug in 27, which tells me the slope of the tangent line is 1 over 27. Therefore, my tangent line is y minus 3 equals the slope, as always, times x minus 27. Now I can plug in 28 in my tangent line, which is a lot easier than trying to plug in x equals 28 in this function, right? So f of 28 is going to be approximately 1 over 27 times 28 minus 27 plus 3 equals 82 divided by 27. So it's a rational number. We could work out using just elementary school elementary school ideas, what 82 over 27 is. I'm not going to force us to do that, so 82 over 27 is 3.03704. But the fact is we could find this number without a calculator. So is that good? If we use a calculator now to look at what the actual value of cube root 28 is, we find that it's 3.03659. So very, very close, I would say, like 0.001 away. Question B here is a very important question for AP Calculus AB. It comes up a lot. The question is our answer an overestimate or an underestimate of the actual value? So we need to imagine now that we're back without a calculator. Of course, with a calculator we see that our estimate was a little bit of an overestimate. 3.037 is a bit more than 3.036. So I know it's an overestimate, right? But let's assume we don't know that. Let's assume we don't have a TI Nspire. How can we answer this question? And the way to do that for AP Calculus AB is to study the concavity of the function. If we take the second derivative, we will realize that the second derivative is, let me think for a second, is negative 2 over 9 times x to the negative 5 over 3. So for any value of x between 27 and 28, we will realize that our function is concave down. We can also see this on the graph. It's concave down always. Why is that important? Well, it's important because if I have a function that is always concave down, then my tangent line is always above the function, right? And that means when I made an approximation, so here we would be at x equals 27, and I calculated the value of the tangent line for x equals 28, I am actually above the function itself. So that means the result I got using my tangent line is an overestimate to what the real cube root of 28 is. It's impossible to draw it clearly here, but you can maybe imagine that the tangent line is above the curve, and so the value I would get, the value I got, has to be above the actual value of the cube root. And likewise, if the function we had was concave up, then it would be the opposite. Our tangent line would be below, so our output value using the tangent line would be an underestimate. It would be less than the real value on the curve. So the way to answer this question on an AP Calculus AB exam is our approximation is an overestimate because f of x equals cube root of x is concave down on the whole interval between 27 and 28. Okay, that's it for this section on finding approximations. Thank you so much.